We're dealing with a knowledge area chemical change. Let's look at other chemical reactions types in a water solution. Let's review briefly what we have done in the previous lesson. Chemical equations can be written to show whether dissolved substances are present predominantly as ions or molecules. When the complete chemical formula of reactants and products are used, the equation is known as a molecular equation. Alright, we spoke about that in the previous lesson. And a complete ionic equation shows all dissolved strong electrolytes and their component ions. Right, and then the net ionic equation shows those ions that go through a reaction unchanged, and they are referred to spectator ions. Here we have a reaction, right, in which positive ions and negative ions appear to change partners, and they conform to the general equation here. So let's just have a look at that. So if we look at this here, we know, so that is normally our positive, that's our negative, that's our positive, that's our negative, positive, negative, right? And that's our positive, and that's our negative. What happens in this situation is you got A with its partner X minus. What then happens is the partners can change, right? The partners can change, like we see here. A's partner was X and B's partner was Y. So A changes partner, and we see that it has a different anion attached to it. So this type of reactions in which ions exchange are normally called ion exchange reactions. Now let's look at ionic equations, and they are useful in summarizing. What they do, they summarize the reaction between acids and bases, reaction between acids and metals, and also between metals and non-metals, and also give us an indication of the ions in electrolytes, and then the precipitation of insoluble salts, which we dealt with in the previous lesson, but we'll also touch on it in this particular lesson. Right, now ion exchange reactions in aqueous solutions. Okay, so an ion exchange reaction, the positive ion of one compound joins with a negative ion of the other compound. Right, now let's illustrate that with a few of the reaction types that we have. So here we got sodium chloride in solution and silver nitrate in solution, and they react to give us silver chloride, which is insoluble. As you can see, I've indicated it by showing that it's a solid, and then we have sodium nitrate in aqueous solution. So if we look at this here, you can see the anion of sodium is chloride and the anion of silver is nitrate, right? So what happens when this reacts, we find that the ions exchange. That means sodium combines with nitrate, and as you can see there, the ions the positive ions have changed their partners. Right, now in this type of reaction, you know that if it's a precipitation reaction and a solid is formed, and this solid is insoluble in solution, it's actually the driving force of this type of reaction. Right. So that formula that we have, this formula that we have here is a molecular formula. Now let's look at the ionic formula for this. So in an ionic formula, we take, so we say the ionic equation. In an ionic equation, we take all the electrolytes and separate them into their ions. Right, so we know sodium chloride is soluble, and so we have sodium plus, right, plus right, plus Cl minus aqueous. And then silver nitrate is also soluble, so we can write that down in its respective, using its respective ions. And then Cl as well. And that gives us, then we have Ag, silver chloride, but that is not soluble, so we write it in its molecular form like that. And Na is soluble, so we write it in its ionic form. Okay, so this is the ionic equation. Now, if we want the net ionic equation, right, we look at the ions and we see, okay, we've got now, and this equation is balanced, we've got Na there, and we've got Na plus there, and we've got like I've made an error here. That was NO3 minus aqueous, right? Okay. So Na, we've got Na plus there, we've got nitrate here, and we've got nitrate there. Okay. So when we look at this now, these ions, the sodium ion and the nitrate ion, are referred to as spectator ions. Right? Spectator ions. Right, they appear on both sides of the equation, and they are not contributing to the net effect of this overall reaction. So if we then look at it, what are we left with? We have Ag aqueous plus Cl minus aqueous. Right, that's in solution, these ions. And when they in solution, we find that they form AgCl solid. Right, so that's the net equation, which illustrates that overall it's the Ag ions plus the chloride ions that combine to form the silver chloride. Right. So we could have any other source of Ag plus ion and Cl minus ion, and if they in solution, they would combine to give us AgCl solid. Let's look at the next one. Right? Here again we've got this precipitate reaction. So what have we got here? We've got, that's its partner, and that's potassium's partner. So what happens is they change, as you can see here. So barium's partner becomes the sulfate, and potassium's becomes a chloride. Okay, so if we look at that reaction is balanced. So let's look at now the ionic equation for this. Ionic equation, right? And it's not the net ionic equation, it's just taking all the ions into account that's in this mixture, which would mean Ba2 plus we got 2 chlorines, but we know chlorine has a negative charge, the ion, and plus K2, so we know K2, K is plus 1, but we've got 2 of it, plus SO4, 2 minus. You need to ensure that the charges are when these charges, like for instance, potassium has 2 plus and SO4 2 minus, that whole ionic substance is neutral. So ensure that that neutrality is maintained by putting your charges on the respective ions appropriately. Then we have BaSO4, it's our solid. And then we have K, which is 2K, right? Plus aqueous, and plus 2Cl minus aqueous. Okay. Right, so that's our equation, and if we look at it, is it balanced? Yes, it is balanced. If we look at our charges, 2 positive, 2 negative, right? 2 positive and 2 negative. So this side, as far as charges are concerned, it's neutral. And on the right hand side, it's 2 positive plus 2 negative. It's also neutral. Now we go to our net ionic equation. Okay, that's our net ionic equation. If we look at our net ionic equation, let's see which are our spectator ions. So we see here we've got chloride, we got 2 chlorides there, right? And then we have our potassium here, and we have our potassium there, right? Ions. So then our net ionic equation is Ba2 plus aqueous plus SO4 aqueous, that's in solution, and when they're in solution they form the salt BaSO4 solid, right? Which essentially tells you that if you have Ba2 plus ions in solution and sulfate ions in solution, irrespective of what the source of those Ba2 ions are, right? Here in this case, your Ba2 ions are from barium chloride. But if we had another barium salt, like for instance barium bromide, and if that's soluble as well, we could use it, because essentially the net ionic equation is telling us that if you have Ba2 plus ions plus SO4 2 minus ions, you then get BaSO4. Right, now let's look at a gas forming ion exchange reaction, and the one we're going to look at is an acid plus a carbonate gives us salt plus water plus carbon dioxide. Right, so if we look at this here now, we have sulfuric acid, here, and we've got potassium carbonate, right? And here we have the molecular equation for it, and if we look at this equation, is it balanced? Yes, it is balanced, right? So the equation is balanced. Now if you want to know what the ionic equation for this is, we say okay, the ionic equation for this would be well, we know our acid now, and how we break that up. So we got 2 hydrogens, so it's 2 plus sulfate and then our potassium carbonate, which is also soluble, so it's 2K plus okay, and that then gives us 2K, okay, that's also soluble, plus SO4 2 minus, right? Then plus H2O, it's a liquid, in liquid form, and it's a molecular substance, so it doesn't break up. And then we have plus CO2, which is a gas, is also a molecular substance, right? So it doesn't break up into ions. And then if you want the net equation, right? So if we look at this now, we say, all right, what have we got? We got K plus there. What else have we got? We got sulfate there. We got sulfate there, right? And these are regarded as spectator ions. Then what are we left with? We are left with 2H plus, right, plus CO3 2 minus, which then gives us H2O plus CO2 gas. Right. So if you look at that, the equation is balanced as well. You got 2 hydrogens on the left and you got 2 hydrogens on the right, right? So whether the hydrogen is in ionic form, it doesn't matter, but you've got 2 H's on the left and you got 2 on the right. You got 3 oxygens on the left and you got 3 oxygens on the right. So what is this really telling you? This is saying that if you have an acid, because when an acid dissolves in water, it forms H plus. So when you have an acid and you have a carbonate, irrespective of which carbonate you have, it will form water plus carbon dioxide. So like I said earlier, writing these ionic equations and the net ionic equations helps to summarize these particular reactions. Now let's look at the acid-base reaction. Right, we're looking at the acid-base reaction. So if we look at the acid-base reaction here, that's the driving force for this reaction. Okay, driving force for this type of reaction is a proton transfer. Right, so let's see. Here we have an acid, right? You know how to recognize an acid. An acid is recognized by a hydrogen that is bonded to an anion, right? And we have dealt with this. So that's how we recognize it. A base here, in this case, we recognize it by its OH. So an acid plus a base gives us salt. That's a salt, and you know what's a salt? Any metal ion with an anion gives us a salt and water. So here we have it. Here, if we have HCl and it's dissolved in water, what happens? We know we get H plus and Cl minus. If we got an NaOH and that dissolves in water and it's an electrolyte, what does it break up? It breaks up into NaNOH. And so, and here as you can see, that's in a molecular form. We've got it there, gives us that. Now let's look at it in its ionic form. Right. So we have ionic equation. The ionic equation here would be, now HCl breaks up into H plus plus Cl minus. Okay. And then NaOH, Na breaks up into Na plus plus OH minus. Right? And then we know we get salt plus water. Right? So plus Na plus aqueous plus Cl minus aqueous, plus the water doesn't break up, it's a molecular substance, so we leave it in that form. Right, now if we look at this here, and we say, okay, the net ionic equation, the net ionic equation, the net ionic equation here would be, and if we look at this, and here we see that we have Na there, Na there, Cl minus here, Cl minus there. So what's our net ionic equation would be then equal to it would be H plus, it would be H, it would be H plus, right, aqueous plus OH minus aqueous, right, and that gives us H2O, liquid. Right, as you can see, you have now your net ionic equation, which essentially says that the H of the acid and the H of the acid and the OH of the base react to give us water. Right, that is a net ionic equation. Right, now let's look at a redox reaction. All the others that we dealt with are ion exchange reactions. Now let's look at redox reactions. The driving force for this particular reaction type is a transfer of electrons, right? So the greater the tendency for electrons to be transferred, that actually drives redox reactions. So if we look at maybe how electron transfer affects the overall charge. Right, let's look at this. Here now, what I have is zinc. As you can see, we've got zinc here, and what's happening? Zinc is placed in copper sulfate. So after a while, what actually happens is you see that in solution here, you have zinc sulfate, and you see copper actually forming. Right, the copper atoms forming. So as you can see, there's your copper there. That's your copper solid. Right. That's the copper solid. So what you have essentially is you have zinc, which was a solid, and it's an atom. I mean, it's neutral, and then you got copper sulfate, which is your electrolyte, and then what happens is you find that your zinc becomes zinc sulfate. That means it's now an ionic substance, and it's an electrolyte, and you find that copper, which was copper in this copper sulfate, has a 2 plus charge. It has then become a neutral species. So if we look at this here now, and we, that is our molecular formula. So let's look at the ionic formula. Right, so we have now, we had zinc, so let's look at that. So we got our ionic equation, okay, ionic equation, okay, and if we look at this, we know we had zinc. Zinc is a solid in here, right, and then we got copper sulfate, which means copper has a 2 plus charge in that in copper sulfate, and sulfate has a 2 minus charge. Is that not so? Right, and then what happens it gives us zinc sulfate. So that goes into solution. So we have Zn2 plus aqueous, right? Plus we have SO4 2 minus aqueous, right? And then we have copper solid, right? If we look at this now, and let's say we want the net ionic equation, the net ionic equation right? So which means in this situation now, let's see, we've got there's a sulfate, it's our spectator ion, and if we look at our net equation, what do we get? We see that we got Zn, the solid. What has become? It has become Zn2 plus, right? So we know when it's in a solid form, it's neutral, and on the other side, it's got a 2 plus charge. And then our reactant Cu had a 2 plus charge, right? And then on the other side, we find that it has formed a solid. So this is an electron transfer reaction. How do we know that? We can see zinc in this in a solid state, it's neutral, and then when it formed zinc sulfate, it's 2 plus. So what has happened? It has actually lost, right there. It has lost electrons. Right. And here, when we look at copper, it's actually 2 plus, right? And what has happened? It has now become neutral. So what has happened? It has gained 2 electrons. 2 electrons. So this is an electron transfer reaction. You could even have determine that by looking at the molecular formula. Here you can see that zinc is neutral. In here, let's go further up. Here, zinc is neutral, and what it has no charge, so I'll reflect it as 0. And here in this, because it's an ionic substance, zinc is 2 plus. So we know that the zinc has lost electrons. Here copper is actually 2 plus, right? As you could see when we broke it up. And here it's neutral. So here it has gained electrons, and there it has lost electrons. So you could identify this reaction, the type of reaction, without even doing the ionic equations. Right, now let's look at gas forming the electron transfer reactions. Remember, earlier we had gas forming with carbonates, and that wasn't an electron transfer reaction, that's an ion exchange reaction. Here, we also have a gas forming reaction, but it's essentially an electron transfer reaction. So here in this case, I've got the metal NaCl, and it's going to react with HCl. Or I have iron, here's the iron reacting with HCl. In both these situations, you see bubbles, right? And that bubbles that you see is actually hydrogen gas, right? It's hydrogen gas. So let's look at the first one. Here we have HCl, right? We have HCl. And that reacts with N is solid, right? So that's our molecular formula, and is balanced. So let's look at our ionic equation. Let's change that. Let's say ionic equation. Right, if we look at our ionic equation, and if we take all our ions into account, then we say, okay, we got 2 HCl, so it's going to be 2, it's going to be 2H plus aqueous plus 2Cl minus aqueous plus 2Na solid, right? That's a solid, and then it becomes 2Na plus aqueous. We break that up since it's an electrolyte, plus 2Cl minus aqueous plus H2, which is a molecular substance. And when we look at this here now, what do we see? We say, all right, I've got that, so I've got that. And is there anything else? No, so we see the chloride ions are spectator ions. So what would our net equation be? Our net equation would be, say, our net ionic equation, our net ionic equation, okay, would be then 2H plus aqueous plus 2Na, the solid, which gives us, right, 2Na plus aqueous plus hydrogen gas. Right, there you have it. So what is this net ionic equation telling us? It's telling us that if we have H plus, and we know what's the source of H plus, and acid is the source of H plus, right? An acid is the source of H plus, because an acid, when it dissolves in water, it forms H plus in solution. And if we take a metal, right, so it's a metal plus an acid, and that would give us then 2Na, right, plus hydrogen gas. So it could have been 2H plus with a different metal, and it would still give us hydrogen gas. Let's illustrate that with the next example. If we look at the next one, here again we've got a molecular formula. Is it balanced? Yes, it's balanced. Let's look at the ionic formula. Right, the ionic formula here, or the ionic equation, right, which would mean, if we look at this here now, we've got 2H plus aqueous plus 2Cl minus aqueous plus we got Fe solid, and that then forms Fe2 plus aqueous plus 2Cl minus aqueous plus H2 gas, right, plus H2 gas. And if you look at the net equation or the net ionic equation, net ionic equation here, you say, okay, let's go back again there. You say, right, what have we got? We got chloride, there again. Then we left with 2H plus aqueous, right? Again, showing you you've got that H plus from the acid plus Fe solid, right? Which then gives us Fe2 plus aqueous, right? Plus H2 gas. Right, again, it's a metal plus an acid, right? Had I used, instead of hydrochloric acid, had I used sulfuric acid, then it would still have generated H plus, right? It would have still reacted with FeS. But here now, I would still have my Fe2 plus ion. But the anion, if I use sulfuric acid, would be sulfate. Because I've used hydrochloric acid, the anion was chloride. Had I used sulfuric acid here, H2SO4, then here I would have had FeSO4. Follow? So, but that ion there would still be the same. Right, now let's look at this exercise. Which of the following are ion exchange reactions and which are redox reactions? Okay, which are ion exchange reactions and which are redox reactions? Okay, now let's look at the first one. Here, firstly, you got K2SO4 plus BaNO3 which gives us barium sulfate and KNO3, right? So let's look at it. You can see here you got, for instance, the partner of K2SO of K plus is SO4, and here that partner is BaNO3. So what has happened? K2SO4, then as you can see here, what happens is K, right, exchanges partners, and K there links up with NO3. So there you can see KNO3, and here Ba then links up with the anion of potassium there. Okay, so this is an ion exchange reaction. Right, that's straightforward, but we want to write an ionic equation for it. So if you want to write an ionic equation for this, ionic equation, right, which would mean if we have that, again we say K, so it's balanced, so 2K plus, like that, plus SO4 2 minus, plus Ba2 plus 2NO3 minus. Be careful, right? Because two nitrates, each nitrate got a negative charge, so 2 of that will be negative 2 plus a positive 2 of barium would then be, it would be neutral. Okay, so be careful about that. And then that gives us BaSO4 which is a solid, right, plus 2K plus aqueous plus 2NO3 minus aqueous. Right. So if we look at this here now and we say, okay, what do we have? We say, all right, we've got 2K. We got 2 nitrates. We got 2 nitrates, right? Those are our spectator ions. So if you look at that, then look at our net equation, net ionic equation, right? Which would then be SO4 2 minus aqueous plus Ba2 plus aqueous. And what does that give us? That gives us BaSO4, the solid. There you have it. Right. Let's look at the next one. Right? So that is then an ion exchange reaction. Let's look at the next one. Here we got zinc, right? Zinc. So we got our molecular equation, and let's look at the ionic equation, right? And this also forms a gas. Okay, it also forms a gas. So if we look at our ionic equation for the, but before looking at the ionic equation, we see that's neutral, right? Here in this case, it's in an ionic form, so we know it forms an electrolyte, so it forms Zn2 plus, which already tells you that it's neutral and it became 2 plus. That means it has lost electrons, right? And here, in this case here, we know that hydrogen HCl in hydrogen HCl, we know it's ionic, so it breaks up and it forms a plus one. And here hydrogen is neutral again, right? So with zinc, what happens? It loses 2 electrons, and hydrogen, the ion gains electrons to form H2. But let's do the ionic equation for it. Okay, let's do the ionic equation. So here we have, if Zn, okay, is the solid, HCl is our electrolyte, so it forms H plus aqueous plus Cl minus aqueous, but we know there's 2 of them, so we have 2 there, and that gives us Zn2 plus aqueous plus 2Cl minus aqueous. So be careful there again, right? Because that 2 and 2 minus 2 there, that whole thing becomes neutral, plus H2 gas. Right. Now if we look at this here and you say, okay, if I look at, I see that I could cancel, that I could cancel, it's my spectator ions. Being my spectator ions, what am I left with? There's zinc solid, right, plus 2H plus aqueous. So when an acid reacts with a metal, so remember this comes from the acid, right? When it reacts with a metal, what do I get? I get the Z2 plus ion, which obviously is part of your salt, right? Plus hydrogen gas. Right, so this is a gas forming reaction, but whilst it forms a gas, it's actually a redox reaction. So remember in the earlier one with the carbonate, it also formed a gas, but it wasn't a redox reaction, right? It was just an ion exchange reaction. Let's look at the next one. Here we have now calcium hydroxide, right? Calcium hydroxide and ammonium nitrate. And if you look at this here, you'll see you got calcium, the hydroxide there, and this one has a nitrate. So calcium actually changes its partner there, and it has nitrate in there. So this is an ion exchange reaction, right? But let's just see if we have it in ionic form now. Let's write it in ionic form. So you got ionic form. In the ionic form, so we got ionic equation. Alright, which means Ca2 plus aqueous plus, we know it's NH4 plus aqueous plus NO3 minus aqueous, right? And what does it give us? NH3, and NH3 is a gas and it's a molecular substance, so we don't have to break it up, and it doesn't break up into ions, right? Plus we have C, okay, Ca2 plus, maybe let's just do it here. Maybe let's just do it here. Plus, I'll write it here at the bottom. Ca2 plus aqueous plus 2NO3 minus aqueous, right? And there's a water there, so plus 2H2O, liquid. Isn't it so? Right, so if we look at this here now, and I say, right, if we look at this, then we say, okay, if we look at this here, and if we look at this, we'll see that we needed to balance this. Okay, there seems to be an error here. Let's see, it has to be 2 there, right? And that would then give us the 2H2O, right? So that 2 needs to be balanced, so which essentially means I have to have a 2 here, right? So it's 2, and it should give me 2 nitrate here, right? Okay, 2. Okay, so that makes sense there, which means in this situation now, if I look at it, I've got 2 nitrates cancelling out, 2 nitrates there, and I've got calcium cancelling out with that calcium, and then what do I have left? So I have now my net ionic equation. Okay, my net ionic equation, which would mean I am left then with 2, right, OH negative aqueous, plus I have 2, right, NH 4 positive aqueous. And as you can see, there are 2 negatives there, so that's -2, and this side is 2 positive, that's +2, -2 and +2 cancel out the 0, right? The total charge on the left, and that would then give us NH3 gas, right? 2 NH3 gas. Okay, sorry, so we left that out as well here, which means that was to be balanced is 2 NH3, so that would be 2 NH3, and that is then equal plus 2 H2O liquid, right? Which gives you an indication. If you see, you got your 4 hydrogens plus 6 hydrogens, 10 hydrogens on the right hand side, and on the left hand side you also got 10 hydrogens, right? So see, 2 3s are 6 hydrogens here, and 4 plus 4 hydrogens here, which gives you a total of 10 hydrogens. And on this side here is 2 hydrogens there plus 8 hydrogens, which in total is also equal to 10 hydrogens. So this equation is balanced. Right, now let's look at the next one. Here we see we've got HCl, right? And we want to know if this is also an ion exchange reaction. Yes, we can see this, and we see, all right, here, for instance, hydrogen chloride, its partner was Cl, right? And potassium carbonate is that. What happens? It then exchanges its partners there. So here you see it's potassium chloride. So this is an ion. Ions are exchanged, right? So that's your molecular formula. Now let's look at the ionic equation for this. So this would mean ionic equation, right? Equation would be 2H plus would be 2H plus aqueous plus 2Cl minus aqueous, right, plus 2K plus aqueous plus CO3 2 minus aqueous, right, which then gives us 2K plus aqueous plus 2Cl minus aqueous. Then carbon dioxide is in molecular form, so we leave it. It remains in molecular form. And then we have H2O liquid, right? So there we have that overall, but if we want to now have the net ionic equation, right? If we want a net ionic equation, so the net ionic equation, okay, what's the net ionic equation? And the net ionic equation in this situation would then be, let's look at that. So we say, all right, I've got that, I've got that, I've got that, and I've got that, and that, right? And therefore now my net ionic equation is 2H plus 2H plus aqueous 2H plus aqueous plus CO3 2 minus aqueous. And what does that give me? That gives me CO2, a molecular substance, plus H2 gas. Right, and as you can see, let's just have a look at that. Sorry about that. That gives us plus H2O. Right, I was wondering where the other oxygen went. So that's the H2O. So on this side, I've got 3 oxygens and the 3 oxygens on the left. So what is this telling us? If I have an acid, and I add it to a carbonate, right? That would give me carbon dioxide and water. And this also is an ion exchange reaction, right? Okay, so now let's look at the next one. Here we got sodium, right? Which is neutral, right? That we know is neutral, isn't it? That's neutral. And here this is also neutral, right? But here, if I just tease this out slightly here, NaI, we know in here Na is plus and we know I is negative. So what has happened? If this is neutral, it then became positive. If it became positive, that means it lost an electron, right? Lost an electron. And this is neutral, but here it becomes negative. So what does that mean? It gained electrons. Right? So this is a redox reaction. Okay. Okay, now it says which of the following is an acid-base reaction and which is a redox reaction. Right? Which is an acid-base reaction and which is a redox reaction. If we look at this here now, you know, when we're dealing with so we got write a molecular equation. Anyhow, the molecular equation has been already given. So you got the molecular equation, and here you can see we dealing with an acid, and there we dealing with a base. So we already know that this is an acid-base reaction, right? And this one here, it's an acid, right? And if we look at Mg, we know Mg is neutral, right? But in here, Mg is going to be 2 plus. So it already gives you a hint that electrons have been lost by the Mg metal, right? So if we want to now write the net ionic equation, we can then write the net ionic equation. So let's say, for instance, for A, we can say, okay, 2H plus aqueous plus SO4, 2 minus aqueous, right? And that plus 2Na plus aqueous, right? Plus 2OH minus aqueous, which then gives us 2Na plus aqueous plus SO4 2 minus aqueous. Right, so SO4 2 minus aqueous. And if we look at this here now, we say, all right, we've got that. We've got sulfate. So we got sulfate there, and we've got sulfate there, right? And then we got 2Na there, and we got 2Na there, right? So what does our net equation become? It becomes 2H plus aqueous plus 2OH minus aqueous. And what does that give us? I forgot to put that. And that's plus H2O liquid, 2 of it. So it then gives us 2H2O liquid. Right, so essentially your acid-base reaction is the H plus of the acid and the OH of the base, right, gives us water. All right, let's look at the next one. Here we have now, so let's look at this one here, okay, and if we look at this, it's B, so we got now, so this here was our net ionic equation, okay? Okay, so here now, if we look at the next one, again we're going to have, for that, we're going to have 2H plus, we're going to have 2H plus aqueous plus SO plus SO4 2 minus, right, same like the above, plus Mg solid, and what happens here, we get Mg2 plus, okay, that's, and then S plus SO4 2 minus aqueous, right, plus hydrogen gas. So if we write the net ionic equation here, net ionic, okay, ionic equation, we have, and if you look at this, we say, all right, I got my sulfates there, I got my sulfates there. Can anything, are there more spectator ions? No. So we say, right, which we have 2H plus aqueous plus Mg solid, and that gives us Mg2 plus aqueous plus H2 gas. Right, and this gives you also a clear illustration, but you could infer that from the molecular formula. So here it's neutral, right? It's neutral, and there it's 2 plus. So what has happened? It's lost 2 electrons. Then here it's a plus, and there it's neutral. Right? And when something is plus and then it becomes neutral, we know that it gains electrons. So this gained. This gains electrons. Right, so this is clearly a redox reaction. And in a redox reaction, if one species is losing electrons, there must be another species that gains the electrons. Right, and that answers our next question. It says, can oxidation occur without an accompanying reduction? What that nearly means, oxidation is uh, oxidation is when we have our metal losing electrons. So the species that lose electrons, we say, undergoes oxidation, right? So what we in essence saying is, can we have one species losing electrons and the other one gaining electrons? Can one lose and the other one cannot gain electrons? No, that doesn't happen. If one loses electrons, some other species have to gain electrons, right? So we would say no, right? If electrons are lost, right, or donated by one species, right, okay, species, another species will gain the electrons. So it cannot happen in isolation. One species donate electrons and the other species gain electrons. You will hear the term in grade 11, oxidation, what it means, and reduction, what it means. So it's redox, reduction, oxidation, right? Oxidation is the loss of electrons and reduction is a gain of electrons. Okay, there you have it, and see you the next time.